Well, my name's Mike Weaver, Associate Director of Sigma-HSE, and I'll be talking about building a basis of safety when working with flammable dusts. This is designed for the EU, and hopefully I've covered bits of this for America. Sigma-HSE Group, well, we're a group of companies based in the UK. That's our head offices, and we provide technical services, health, safety, and environment. We have 3 units: Sigma-HSE UK, Sigma-HSE in India, and also Sigma-HSE USA. We bring together our UK, Indian, and USA experts to provide clients with global HSE services, and we try to give you cost-effective engineering solutions. In our laboratory in the UK, we undertake laboratory testing to BS-EN and ASTM standards. Technically wise, highly qualified staff, engineers, scientists, and chemists, experienced professionals in their field, and some of us sit on standards committees. We've worked with global industries all across the world, and these sectors include pharma, food, chemicals, oil and gas, utilities, and the list goes on. We look at dust, gas, and vapor, fire and explosion testing. We cover electrostatics. We have our own electrostatics test lab, chemical reaction hazards laboratory, and we work within ISO EN 17025 quality accreditation, and we are the only UK company that has that. Our consultancy team provides a wide range of specialists and knowledge covering the following sectors. So we look at our industrial fire and explosion hazards, which complements our laboratory, electrostatic issues and problems, hazards, PHA, QRA, hazard, HAZOP, PSM, etc. Functional safety for safety integrated levels, layer protection analysis, DEERS calculations for runaway chemical reaction, and we do training workshops, both public and in-house, along with other things such as this webinar. So, first steps, developing a basis of safety. How do we progress with it? How do we choose the right basis of safety when we look at our processes? First thing you have to know is, what is a basis of safety? It's a combination of measures relied upon to ensure safety. So it's not one thing, it's a combination of things, and you put them together to ensure that you're safe for working. It takes into consideration the aspects of design and operation that are safety critical, and therefore an overall safety strategy can be applied to any of the following. You can look at the equipment, the process, areas where the equipment is located and the process is working, and work instruction that you hand out to people. So this would be in the form of SOPs, for instance, or it could be machinery supplied by the supplier. In order to build any basis of safety, it is necessary to have specific information available. And some of the things you'll need are the equipment specifications. I talked just now about standard operating procedures. How do you work with this equipment? How do you produce the product that you're dealing with? Hazardous area classification. How have you zoned the areas where the equipment is located into hazardous areas? To do this, you need quite a lot of expertise to do the job safely. And many a times I've walked on to plant and seen hazardous area classification drawings, but no report. And you really do need a report to go with it to explain the logic of how you arrived at a particular zone, whether it be a zone 0, 1 or 2 for gases and vapors, 20, 21, 22 for dusts. Maintenance procedures. How do you look after your equipment? Are you reactive in its maintenance, or do you carry out a preventative maintenance structure? What materials are being handled? Are they liquids, gases, powders? Do you know anything about them at all? You'll need flammability data, such as MIE, MIT, LIT, KST, PMAX, etc. We'll talk about that in a few moments. Always note as well that the world is shrinking. We are getting products now from areas such as China, Korea, Africa, and South America, and North America, etc., and Europe. So with a world shortage of materials, many companies are turning to these new suppliers. This means that some of the material properties may change, and is therefore advisable to consider retesting these products. A good indication of that, for instance, is coal. The coal that is produced in Europe has MIEs probably 100 to 150, and we've tested some Chinese coals which are less than 10 millijoules. So don't think it's just coal or it's the same product you've always used. It may have changed with its physical properties. So we're trying to build an effective basis of safety. So how do we make this decision? Where do we start? Well, we need a few things to put into it to find out what comes out at the other end. So the first thing to look at is what types of equipment are we using? Blenders, sieves, mixers, big bags. The next thing we need to do is look at SOPs, operation procedures, operators' instructions, or the equipment manufacturer's instructions. How do these apply to the situation we're looking at? How do we train our staff? How do we make sure they understand these things? Do we deviate from normal operating conditions or processes? Oh, we're just Friday, we need to get this material out. So we'll just increase the temperature by a few degrees. Or we'll speed up the mixer a bit so we can get the product out quicker. These are deviations from normal. Or we're just going to add this other small amount of ingredient, but you haven't looked at to see what happens if that small amount of ingredient is added to your process. This has to go into the basis of safety. Human factors. This is a big question. With humans, they can be absolutely brilliant. If you look at a human and a guy who's worked on a machine for 20, 30 years, he can sense if something's wrong. The noise isn't quite right, there's smoke, or he's got this feeling that things are not quite right, and he needs to get somebody to come and have a look at it. On the other hand, they can do the most stupid things that you could ever consider. And one that I dealt with was 2 vessels, A and B, and they were cleaning vessel A, and they switched off the ethanol, and while they were working, they started up the other process, which was process B, and they pushed the button to let the ethanol in, and instead of that, it came in to A instead. Someone had programmed it in wrong. And this is human factors. So sometimes they can be brilliant, sometimes they can do the most stupid, ridiculous things that you could ever think about. And I've certainly seen a few of those. So material properties. As I said, here's some signs here with the icons that you'll see on lorries or vessels. These are the standard sort of signs for toxic, environmental, could be flammable, explosive, etc., etc. But also on top of that, there are things which are completely to do with fires and explosions, such as minimum ignition energy, layer ignition temperature, etc., which we'll talk about later. Risk level and tolerance. How much risk are you willing to take? No process is 100% risk-free. Every process that you work with will have some level of risk. If you don't want to put up with that or understand it, then go home. Go to bed, and just remember, if you do a risk assessment, 90% of deaths occur in bed. So make sure you do your risk assessment correctly. And there's many more things that can go in to form a basis of safety, which may be specific to your process, that you may feel that they need to be added to make sure the basis of safety is robust. There are three types of basis of safety for fires and explosions, and each one of these that you choose will be dependent on many things like I've just shown you. And when you've selected your correct basis of safety, you have to prove that it's suitable for your process and that you haven't missed something out. So you could start off with explosion prevention, achieved by avoiding flammable atmospheres. Difficult in a lot of cases with dust in particular. With gases and vapors, you could work below the LEL or above the UEL and avoid the flammable atmosphere. You can use nitrogen inerting in these instances, but again, this system has to be robust and you have to make sure that it works correctly and no guesswork involved with it. Avoidance of ignition sources. The only way you can do this is to make sure you have all the information on what it takes to ignite your product. In other words, avoid sufficient energy to ignite an explosion. Will ignition source become active? And if it does become active, will it become effective? If the first two can't be chosen, you've looked at it and it's not 100% sure, then you would work in with explosion protection. Explosion protection will not stop the explosion. What it will do is reduce the damage done to plant and protect employees from the explosions. So this is one a lot of people use, even in the food industry, explosion protection. And this could be, any one of these could be combined, that you think to yourself, 90% of the time, I can get away with avoidance of ignition sources, but I'm still going to fit explosion protection for the other 10%. So what causes a dust explosion? What are the conditions for it? Well, the dust must be flammable, combustible, and it has to be airborne to form a dust cloud. Powder layers can be generated into a dust cloud. So again, try to reduce the possibility of powder layers existing on the plant, as anything like vibration, wind, or changes in the environment could make these into a dust cloud. When it comes into the dust cloud, the concentration must be within explosible limits. Unlike gases and vapors, there are no UEL, upper explosion limits, for dusts, mainly because you generate the dust cloud, which may be extremely dense, but over a period of time, the dust settles. The most important value here is the lower explosion limit, or MEC, which we'll talk about later. Particle size distribution should be capable of propagating a flame. Normally, we look at the fact that if you're below 500 micron, then it's highly probable that you'll be able to generate a flammable dust cloud. Above 500 micron, the particles are normally too large to create a flammable dust cloud. In the atmosphere where the dust cloud is present, looking at oxygen, needs to support combustion. So normally we look at normal air, and that's basically roughly 21% oxygen. And you must have a sufficiently energetic ignition source. So if you look at your materials and you have an MIE of 500, and the ignition source, when it becomes active, only produces 100 millijoules, it's not effective. So we've got the fuel, the ignition source, and the oxidant. This is what we call the fire triangle, the three items you need to create a fire. If we mix the fuel with the air or the oxidant, then the dust cloud is surrounded by the air amongst it. And then we confine it. It has to be confined to form an explosion, otherwise you get a flash fire other than an explosion. So why is flammability testing important? Well, you need to understand the explosive and flammability properties of your materials. How can you pick a basis of safety unless you know how the product behaves? It's required to understand the sensitivity of your materials to potential ignition sources, especially if you're looking at avoidance of ignition sources. The data can also be used to see how far away in normal circumstances you are from a material being able to be ignited when you select explosion prevention, or you select explosion protection, where you need to know the violence of the explosion. Helps you to determine whether you can stay outside the flammable limits. As I said, with dusts, you've only got a lower limit, no upper limit. And lots of people don't realize this, but the United Nations and the GHS system, the Global Harmonized System, in 2021 made dust explosion data a legal requirement for safety data sheets. Thinking back to 2018, when I was sitting on the GHS committee, I had to give a presentation to the people on the committee to get them to understand what a dust explosion is and how much damage they do every year and how many people they kill. And if we look at the sugar refinery in America, this is a very good instance of it. A safety data sheet says what it does on the tin. It is a safety data sheet. Therefore, it should contain information to make sure you are safe, whether it's a liquid, a gas, or a dust. Gratefully, in 2021, they got together and agreed it should go on data sheets. The testing that we do, as I said, with the type of basis of safety, can be divided into three sections: testing for explosion prevention, testing for avoidance of ignition sources, and testing for explosion protection. And sometimes it's good to have, say, the avoidance of ignition sources data to see what sort of animal you're working with. So as I said to you about the data sheets, Annex 2 of REACH has been amended concerning the compilation of data sheets as from the 1st of January 2021, amending it in line with the UN recommendations under GHS, the Global Harmonized System. Legal requirements to include flammability such as MIE, LIT and MIT, PMAX/KST. We'll talk about those later. Lower and upper explosion limits for gases and vapors, MEC for dusts. For gases and vapors, we have the flash point and the auto ignition temperature. And when you see in item 1, the MIT is basically the AIT for dusts. So here's a list of the type of flammability data you can get. You can get minimum ignition energy. This lets you look at the risk of ignition by electrostatic or mechanical spark discharges. Minimum ignition temperature considers the ignition of a dust cloud by hot surfaces. Layer ignition temperature considers the ignition of a dust layer by hot surfaces. Pmax, that's the maximum pressure of an explosion. KST, K is the constant, ST is Staub for dust, so it's a dust constant. ST class, Staub class, used for explosion protection. Minimum explosive concentration considers the flammable range. There's the lower limit, like the LEL. Limiting oxygen concentration is what you'll need as you consider inerting to be for explosion prevention. A lot of people don't bother with this, but I've had some pretty fast powders in the past, which is burning behavior. For transportation, it's necessary, and this determines how fast a material can burn, in other words, the fire risk. Resistivity and charge relaxation time. These two combined look at electrostatic issues and equipment specifications for zoned areas. They're also very useful for floors, gloves, shoes, etc. Thermal stability, ignition risk from thermal decomposition. So if you're drying, whether it's a spray dryer, whether it's a fluid bed dryer, etc., you need to know how safe you are on that drying. Now, some people do things like DSC, differential scanning calorimetry, but this is not suitable. The main thermal stability testing mimics the type of operation that you're doing. So we would have tests that mimic a spray dryer or fluid bed dryer or a ribbon dryer, etc. And then we can give you safe working temperatures. And the same for storage. Many instances I've attended where silos or storage hoppers have caught fire because they've been working even 2 degrees above the safe operating temperature. So let's look at explosion prevention. Well, the first thing we're going to have to do is look to see if it's Group A flammable or Group B non-flammable. Here you see the MIE apparatus, which has always been used, but today the standards tell you to point towards the 20-litre sphere test to confirm this exactly. And we'll talk about the 20-litre sphere test later. Nearly all these tests are covered by 80,079-20. So limiting oxygen concentration. When we look at this, we look at the minimum allowable concentration of oxygen in a mixture of dispersed combustible dust in air and an inert gas, in which an explosion will not occur. Generally higher than for gases, can be typically 10 to 15%, but some materials are much lower. Examples are for nitrogen as the inert gas, though we can do a conversion over for things such as CO2. Some examples on the right-hand side: rye flour 13, organic pigments about 12, methyl cellulose 10, beta-naphthol 9.5, sulfur 7, paraformaldehyde, now we're coming down 6, aluminium 5. Aluminium lithium hydride used in batteries is about 3. Look at the minimum explosible concentration. This is the minimum quantity of dust dispersed in air that is required to form a flammable atmosphere. As I said, similar to the LFL or LEL for gases and vapors. And it's measured in the 20-litre sphere. Conducted to BSEN 14034, and it's tested in our laboratories. And some bright spark, and I don't know who it is, comes up with a suggestion that 40 grams per cubic meter of coal dust, you can't see, or you're struggling to see, a 25-watt light bulb from 2 meters. So it's a pretty dense dust cloud to support combustion. Avoidance of ignition sources. What you're seeing here is what's given in EN 1127, which are 13 potential sources of ignition in any process. Normally, and I say this with experience, normally most processes we tend to look at just a few. Hot surfaces, flames, smoking and hot work, mechanical friction and thermite sparks, electrical apparatus, exothermic reactions and spontaneous combustion, and static electricity. For your information, thermite sparks occur when aluminium is in contact with a surface like rust. In other words, if you have a ladder, an aluminium ladder, and it strikes against a rusty beam, a thermite spark can occur. And these are above a joule in energy, so they're extremely incentive. So, as we talked about before, minimum ignition energy. 2 tests are done with this. We have a purely capacitive discharge. This would simulate a person, for instance. We are a capacitor. This looks at electrostatic discharges that can occur. And these sparks are quick, short, and will depend on half CV squared. In other words, the capacitance of the object and the voltage produced on it. So these sparks can go up to about a joule in energy. Inductive discharges. This is where we put an inductor in the earth circuit on this equipment, which makes the spark stay longer across the electrodes. This simulates mechanical sparks. As you know, with a mechanical spark, it seems to stay a lot longer than a purely electrostatic spark. At the end of the day, any ignition source with an energy greater than the material's MIE is capable of providing ignition to the flammable atmosphere. So here's some examples for you. Starch, 100 to 300 millijoules. Glass reinforced plastic dust, 30 to 100. Sugar, 10 to 30. And some very, very fine sugars can be lower than 10. Aluminium can be anywhere between 3 and 10. And active pharmaceutical ingredients could be down to 1 to 3 millijoules. So some very low values there when you look at APIs. These are equate to a gas or a vapor. Then we have the minimum ignition temperature. It's the lowest surface temperature that can ignite the optimum mixture of fuel, which is the dust when dispersed in air. MIT is the auto-ignition temperature for dusts. You get this value, you can use it to calculate the maximum permitted surface temperature of equipment. So it's one of the values you would use when you have a piece of electrical equipment and you need to know its maximum surface temperature. The equipment can test between 200 and 700 degrees C, and the standards are down below. We also test to the American standards ISTM. Then you've got ignition sensitivity for the layer ignition test. This complements the MIT. This time, the layer ignition temperature is the lowest surface temperature that can ignite a 5mm layer of material. In the States, they've opted for 10mm layer. Now the problem we have here, the two are not relatable because the larger the depth of the material, the lower the layer ignition temperature. It was decided within Europe that 5mm is more than enough to be allowed on any piece of equipment. For me, it's at least 5mm too much. The LIT is used to calculate the maximum surface temperature of the equipment. It must be used with the MIT. The value of the furnace or the hot plate here is 200 to 400 degrees. So, most common ignition sources. We saw a list from EN 1127. Let's have a look at some of the more popular ones. Electrostatics. These are mentioned specifically in the ATEX directives, which are used within Europe. The risk is high due to some dusts having a very low MIE. Some values are less than 1 millijoule, which are very similar to gases and vapors. We can look at flames and hot work. The risks from these are high, and ignition will depend upon the MIT of the dust. Hot surfaces. We've got electrical motors, for instance. You may have bearing surfaces. You may even have the temperature of the outside of the equipment, which may be particularly high. The risk is moderate, as many values of MIT and LIT are quite high, although some materials do have much lower values, such as sulfur or sulfur salts. So don't be complacent about it. And if you're dealing with electrical equipment, you'll need to confirm that the maximum surface temperature of enclosure is selected correctly. And these two tests, MIT and LIT, will give you that property. Electrical sparks. All electrical equipment must be suitable for use in any given flammable atmosphere. This should be a given. And really, when you look at hazardous area classification, it started off life is electrical equipment hazardous area classification. So you can see how far back it goes. So hopefully, when you look at your electrical equipment, you can make sure it's safe for use within zoned areas. In the UK, and it's being applied in Europe, we have the COMPEX scheme, where electricians get trained for working in potentially explosive atmospheres. And there are American companies and companies in the Middle East and India, etc., which are taking this idea on board and getting their people COMPEX trained. And then we have mechanical sparks. The risk of ignition is high when you have a very low value of MIE and combine that with a low value of MIT. If we look at dust explosion ignition risks, then you'll see roughly worldwide about 40 dust explosions annually. it doesn't seem to go down. We still seem to be getting them. This results in injury and loss of life. You end up having to repair your plant, which means you can't run the plant, which means you can't produce, which means you can't sell and you can't earn money. Also, compensation for it and your reputation. Nobody wants to work with a company that has just killed 2 or 3 of their people. It has business interruption and loss of market. And of course, you've got the insurance companies that once you've had an explosion are going to be a bit reticent to insure you. And if they do, they're going to come on site and check you out with a magnifying glass. If you look at the sources of ignition above, you have mechanical, as I said, you got different sparks, friction, grinding impact sparks, overheating. Again, I talked about thermal stability of products, for instance. This is quite a common occurrence. Open flames, people working with welding equipment and not cleaning out the equipment before they've started to work on it. Electrostatic ignition, again, quite high. People tend to confuse this with electrical and often put the electrician in charge of the electrostatics. It is similar, but not the same. And then you have cases for welding and electrical and other. Means that someone's looked at it and can't come up with any idea of what caused it. Normally the person looking at it is not an expert in the field of fires and explosion, as I found out on many occasions when I've done incident investigations and come up with a completely different method of why it ignited compared to what the plant had assessed. So looking at hot surfaces and temperature class for dust, the maximum surface temperature of the equipment must be less than the MIT or MIT of the worst case material used. Temperature classes of equipment exist so that it can be properly specified for the application, and this applies temperature classes only to liquids and gases. This is T1, T2, T3, T4, T5, T6. For dust, there is just a specific temperature given on the equipment. So if the dust cloud Tmax is less than 2/3 of the MIT, or it is the LIT take away 75K. Normally the LIT is much lower than the MIT because the test goes on for half an hour other than MIT, which is just 10 seconds. So 2/3 the MIT, 75 degrees off the LIT, and this will give you the maximum surface temperature of enclosure for your electrical equipment. Flames, smoking, and hot work. Well, hot work should be controlled by a permit system, a permit to work system. In other words, if someone wants to work with welding, etc., then they must get a permit to work offered to them, and the person that does it must know about the process and know about the risk involved with hot work. You need to make staff aware of the hazards to avoid likelihood of common ignition source problems. Training of staff, very important. Smoking must be banned in hazardous areas and only permitted in designated areas. Often control all access to hazardous areas. With regards to smoking, let's say within Europe, then every site I go on today is only allowed in a designated area, and some sites have banned it altogether. So we don't have this problem so much that we had 20 odd years ago. Electrical equipment for dusts. Well, electrical apparatus in hazardous areas must be suitable for use in the area, depending on the following. So we know the MIT and LIT for surface temperature, so we can decide whether that's going to be a problem. Zonal classification in the area, so Is it zone 0, 1 or 2 for liquids and gases? Is it zone 20, 21 or 22? And again, depending, let's say for a zone 0 or 20, the specification is far higher to stop an ignition. Ingress protection, can you stop the dust getting into the equipment? And the type of powder, is it conducting or insulating? So typical signs that you would see on electrical equipment, the European conformity, EX shows it's in explosives, and then under the 2014-34 directive, you've got Group 2, Category 2 for dusts. Extra data, EX means a certified body has certified the equipment. TB means that's the type of protection. 3C means it's an insulating dust. And there you've got the temperature, one specific temperature. And DB is the equipment protection level, which means this equipment is suitable for zones 21 and 22. The electrical equipment must be installed and maintained by competent personnel. And as I said to you before, in the UK and moving into Europe, America and other areas of the world, people are taking on the compact scheme. So, electrical equipment for dusts in the USA. The USA does not usually have complex training, but works on the IEC EX certification via the NFPA, which is a unit that you work under quite a lot. However, complex training is available, and a lot of international companies are taking it on. So under the aspect that we're looking at is classification basis, is ATEX, IEC, looks at the frequency and duration of explosive atmospheres, and classes and division in North America, the type of hazard and the likelihood of the presence of it. In zones and definitions for the aspects, we have zone 0 and zone 20 is a continuous presence with under ATEX, and that's 0 for gases, vapors, 20 for dust. And under the American one, you've got division 1, which means it's present under normal conditions. And then we have zone 1 and zone 21, again gases and dust, likely to occur occasionally under ATEX. No further definitions in the North America. And the last zone that we would look at, 2 for gases and vapors, 22 for dust, very unlikely for it to occur and only for short durations. And in America, you've got division 2, present under abnormal conditions. The classes of material, so we look at gas. In America, in the EU, we would take gas as being the class. And in the USA, we have class 1, gases and vapors. We have dust in the Europe, and in America, class 2 is dusts. So typical American designations, you see the material type, the area classification, the likelihood of the presence. We talked about division 1, division 2. Material properties, there's a whole range of them there going across, and the temperature classes. So you've got groups B, C, D for the gases and vapors, and a T5 definition for temperature class. And then for the dusts, you've got groups F and G and the temperature, actual given temperature. So the USA material groups defined here: Class 1, flammable gases and vapors. Group A, gases like acetylene. Group B, hydrogen, ethylene oxide, propylene oxide, butadiene. Group C, ethylene, cyclopropane. Group D, propane, methane, acetone. And Group 2, combustible dust. Group E, combustible metal dusts such as aluminium, magnesium, titanium. Group F, combustible dust, carbon, charcoal and coal. In Group G are other combustible dust, such as the food industry, plastic, woods and chemical dust. And Class 3 means ignitable fibers and flying. This class covers ignitable such as cotton, rayon and wood, and is not further divided into groups. So mechanical equipment ignition. 6 potential ignition sources by non-electrical equipment. You've got hot surfaces, flames and hot gases, mechanically generated sparks, and electrical ignition sources, i.e. stray electrical currents, and of course static electricity. In Europe, for equipment in hazard areas, we undergo non-electrical equipment ignition risk assessments, NERA. And this follows the Directive 80,079-36 and 37 for normally 36, but for certain methods of protection, you may need to look at 37. Then we have static electricity. As I said, one of the only ignition sources mentioned in ATEX. And it's mentioned explicitly in the Dangerous Substances, Explosive Atmospheres regulations, which were used within the UK, and ATEX 153, which is used within Europe. Static electricity is generated wherever movement takes place. If you look on the left-hand side, you'll see some pictures there, pouring the powder, liquid going through a pipe. You've got someone walking, rollers, spraying, and then material ending up inside a vessel. Static electricity is often intrinsic to the intended process, and you struggle to get rid of it. You may be able to minimize it, but you won't get rid of it. And it's a very specialized topic. So assessment of static hazards. Do you have a flammable atmosphere? Can you generate charge? Are some of your materials insulating, for instance, and they can generate lots of charge? Can that charge then accumulate? How much energy can it produce? And how does the discharge of that energy work? This is an electrostatic ignition assessment. These are the facts that you're going to need to put together to make sure when you do an electrostatic ignition assessment, you have everything at hand. So we have certain types of discharge. Corona, very low energy, well less than 1. This occurs at a sharp point of an earth conductor near a highly charged object or vice versa. You'll hear this on electric pylons from sharp objects up there having charge induced on them. It's not incentive unless they develop into a spark. You have brush discharges, charged insulator, discharge to earth conductor. Take your nylon jumper off at night, you'll see little areas there of sparks. These are brush discharges. Low energy, 3 to 4 millijoules. They will ignite gases and vapors, but not dusts. I fought for this one for probably 20 years to get people to realize it doesn't matter what the MIE of the dust is, whether it's 1, 2, 5 or 10, you cannot ignite it with a brush discharge. Finally, I got my way, and this has now been included into the standards. Spark discharges. These come from charged isolated conductors such as people and go to earth or can go to another conductor. E equals half CV squared, and they can range from 0 to 100 millijoules. They can ignite gases, vapors, dust, mists, and where the energy is greater than the MIE. You have cone discharges, highly charged insulating powder filled into metal earthed silos, up to about 150 millijoules, and they can ignite gases, vapors, dusts, and mists in where the energy is above the MIE of the dust. The worst situation here are large granules of insulating powder with a fine dust cloud above it. Brush discharges, two surfaces of a high resistivity material oppositely charged, which end up with a short circuit. So you normally have a very thin insulating layer on a metal substrate. In other words, an electrolytic capacitor. They can have energies up to 1 joule, and they can ignite just about every dust cloud, gases, vapors, dust, mist, anything. And I've seen some horrendous damage done from people that haven't realized they've generated propagating brush discharges. So how do we control static electricity? Right, bonding. That's the joining of discrete items of a conducting plant with suitable electric cable. Many items may be bonded together so you can go all the way down the line to reduce the potential difference between the items. Earthing, this is the most important thing, is to ground it to earth with a suitable electric cable. Any bonding run must be earthed at both ends. Typical ground proving unit. So they're connected there to the tanker. And if you get a good earth, the light goes green and allows you to work. If it's red, it stops you, prevents you from working. These are installed in a lot of places, oil refineries, for instance. And funnily enough, a lot of food industry have them. So with earthing of personnel, ground leads can be used, but totally impractical, as you can see with the ball around his feet. Normal approach is to use static dissipative flooring along with static dissipative shoes and clothing. You must remember the total resistance between the body and ground should be less than 100 megohms. So summary of avoidance of ignition sources. Consider all types of ignition sources, but concentrate on the 5 most important. Hot surfaces, flames and hot work, electrostatic, mechanical, and electrical. Perform hazardous area classification so you know what type of equipment you've got to have in it, and make sure the equipment is suitable for that zone. Consider more detailed assessments if you've got electrostatic issues and electrical equipment and you have the risk of mechanical failure. Control all naked flames and hot work by permit systems. Obtain suitable flammability data, as I spoke about before. Understand if a potential source of ignition can become active, and if it does it become effective? And then afterwards write a detailed basis of safety report explaining your process. The final one we talked at is explosion protection. And I put this one up, Imperial Sugar in 2008, 14 deaths, 38 injuries, 14 with life-threatening burns, explosion fueled by accumulations of sugar dust. In other words, I said about the layers, explosion propagation throughout the building, no means of stopping the propagation of the explosion at all. And the company had a very little knowledge about fire and explosion protection for safety. And this is just sugar. So 20 liter sphere testing, from it you get the maximum explosion pressure, the dust constant calculated from the rate of pressure rise in the equipment. The explosion severity data is required for explosion protection systems, such as venting, suppression, or containment, when you decide to take explosion prevention as your basis of safety. And again, conducted here and ASTM standards. The indices ST class or Staub class, 0 no explosion, silica for instance, means it's inert. ST1, 0 to 200, weak explosion, that's the sugar, weak. Powdered milk, charcoal, sulfur, sugar, and zinc. ST2, a fairly strong explosion, 200 to 300, cellulose, wood flour, polymethyl acrylate. And ST3s are the big ones, greater than 300, very strong explosion, anthraquinone, aluminium, magnesium, aluminium lithium hydride, battery dust is the worst one I've ever tested, and that reached 1,200 when you compare 550 for hydrogen. So mitigation of risks. If the risk cannot be eliminated or controlled, then you must try to mitigate the risk. Reduce the number of employees, not possible. Avoid the propagation of fires and explosion, very important. Install explosion relief arrangements, do explosion suppression or containment. And then other things such as personal protection equipment. If several dangerous substances are present, then look at the worst case. Also consider safe storage and transport, including waste. Always remember waste is a product on your site. So in a closed vessel, they create hot gases. And in a closed vessel, the pressure will increase, as you can see, up to Pmax. And the rate it gets there is dPt, and from that, you get the KST. Any protection system must be able to cope with the expansion and or pressure increase with the short time available. So with containment, isolate pieces of equipment where explosions can occur. All isolated plant must be designed to withstand overpressure. No release of combustion products or toxins, which is good. No requirement for safe areas, which is good. On the downside, the equipment is very expensive to build and you need to maintain it as a pressure vessel. It requires pressure testing and all the associated documentation in the equipment can be extremely heavy. So for containment, all the parts of the plant must be made strong, includes pipes, ducts, flanges, covers, etc. And the 27 bolts going around the bottom of the vessel are there for a reason. Don't put in 5 or 6 because it stops the dust leaking out. The 27 bolts are there to stop an explosion coming out. Must withstand the maximum pressure that is expected, and it's got to maintain the vessel's strength over its lifetime. It can either be pressure resistant or explosion shock resistant and have some deformation. Don't forget, strong plant is expensive to build and difficult to operate. Venting is the most common way. Protects plant and personnel from the effects of an explosion. Controlled release of pressure via weak opening sections, and vent sizing is determined from the KST and the Pmax. Gives ability to control the release co-location. It's a passive protection system and can be retrofitted to weak equipment. On the negative side, combustion products and overpressure are released. Non-flameless systems lead to explosion propagation. So venting advantages can be designed in-house, relatively cheap for the vent itself, needs little maintenance, but you need to make sure it's good. Very wide range of applications. The disadvantage is materials are released, so it's unsuitable for toxic corrosives, must discharge outside the building, restricts the siting of plant items as they have to be on the outer wall, and you need large safe areas required. One of the things that's more common nowadays is flameless venting. Special devices attached to the explosion vent area can stop the flame while allowing the venting. Q-roar, flame quench, for instance. Efficiency is reduced compared to normal venting and needs to be type testing. If you have materials like sugar, for instance, caramelization occurs and then it can block up these vents and they stop working properly. Other cases are, don't forget, It stops the flame but releases the toxic materials and the pressure outside. So the flame is prevented from exiting the vent. High pressure and smoke can still fill the workplace. Must be sited in a restricted area. Don't just put them anywhere. One I saw faced a lift. Requires regular maintenance. Must be suitable for processing materials that are either toxic, caramelization, etc. And then you've got explosion relief doors. As you can see there, they open when the explosion occurs and close afterwards. Don't require replacement after the explosion, easy to maintain and cheap to fit. You've got to prevent the door closing too quickly after the explosion, otherwise you end up with a vacuum and the vessel deformation. They can weather badly and therefore robustness can be compromised. Often failure to be maintained, and I've seen them full of bird's nest powder around them. As I said, after closing, this is what happens if the vent closes too soon. You get a vacuum and your vessel is destroyed. So be careful when you're using the doors. Flame propagation. Most of the fuel air mixture will be expelled from the vent and burn outside the vessel. The length of the flame can be predicted. So for dust, you've got a distance of 8 to 10 meters times v to a third. Take a 1 meter vessel, that's 1. Therefore, it's between 8 and 10 meters long, the flame. Not more than 60 meters in length. And for gases, it's 5 times v to a third. The width is not easily calculable. Typical vent problems, leaking and badly maintained vent. I've seen covers on top of vents with weights on top, which have become flying missiles if the vent opens. So maintain them correctly. Suppression systems. They extinguish the explosions in the early stages of an explosion. Injection of pressurized suppression agent at given points, as you can see on the picture on the right. There's no external effects of the explosion suitable for toxics. On the downside, they are reliant on effective explosion protection, highly specialized design, and the product will be ruined at the end of it. So, advantages: no release of materials suitable for toxics, no restrictions where the plant can be located, no flame propagation, well-designed system. It incorporates isolation measures. Disadvantages: often a high capital cost when compared to venting. Needs regular maintenance by the installation company. Only works when operational. After acts of activation, then you need to recharge the bottle and get the installation company back, and loss of product. And don't forget to switch them off if you intend to clean the inside of the vessel. Like one company I went to that complained the guy nearly had his ears blown out when it went off while he was cleaning it inside. Here's some for a fluid bed dryer, and you can see them on there on the dust collector. Isolation, necessary to prevent pressure piling effects and flame gen. Without isolation, the explosion in secondary vessels could be more severe than what their design criteria is. The explosion increases with initial start pressure. An initial start pressure of 1 bar and you had a 7 bar Pmax will now be 14 bar, and so it goes on. And the risk of secondary explosions will occur, as you saw with imperial sugar. Typical isolation, rotary valves, fast closing, slam shut valves, for instance. Don't forget, rotary valves will stop an explosion, but not a fire. So summary for explosion protection. As before, determine the flammability characteristics of materials. Review the safety data sheets to see if you have toxic materials, etc. Review the hazardous area classification so you can identify where the equipment is to be located. Venting and suppression systems need to be designed and installed correctly, as should fire protection. For containment, the vessel needs to be certified for use at expected pressures, and maintenance people need to be trained for pressure vessels. Location may be a problem for venting as it has to go on an outside wall. Confirm suitable isolations in place. And assess special procedures, hot work permits, management of change, permit to works, etc. And management of change will give you an indication whether things have changed within your process and your selected basis of safety will operate still. Personnel working in hazardous areas should be correctly trained and the training repeated. So, overview of formulating a basis of safety. Use a combination of measures relied upon to ensure safety. Highlight aspects of design and operation that are safety critical. Look at items such as equipment, procedures, deviations, human factors, material properties, and level of acceptable risk, and other things you feel necessary to put in. And don't forget, this is not going on for the life of the process. You need to reassess it when any change occurs, or at about 2-year intervals to make sure your basis of safety is still robust and works. So for fires and explosions, explosion prevention, avoidance of ignition sources, and explosion protection. Explosion prevention, several ways, including change the flammable material, remove the oxygen, work outside the flammable range, not really possible for dust, as powders are non-homogeneous. Avoidance of ignition sources, we went through those. Look at the most common ones: hot surfaces, naked flames, electrical, electrostatic discharges, mechanical sparking. Look at material properties. As I said, if you don't know how sensitive a material is to ignition, how can you define a basis of safety for avoidance of ignition sources? If you don't know how big the explosion is, how can you formulate a basis of safety for explosion protection? If you're using inerting, how can you work without the limiting oxygen concentration? Just as a couple of examples. So summary: hazardous area classification, potential ignition sources. If required, look at things in more detail, such as an electrostatic audit, especially if you have a low MIE for dust or gases and vapors are present. Equipment specifications and their suitability for the zone. Operating procedures, the risk assessments you performed, and of course, any incidents that you've learned from. And material flammability, electrostatic, thermal instability properties. Assess the process to understand the manufacturing hazards when you're charging and discharging, mixing. Process maintenance procedures, are they in place for hot work permits, management of change, permit to work, etc. Personnel working in hazardous areas should always be correctly trained and their training updated when any change occurs. Determine what basis of safety can be used and confirm that it's suitable once all the information has been analysed. And don't leave it any longer than about 2 years before you recheck it, and check it if the management of change says there has been a change. Well, thank you very much for listening. Overrun a little bit, sorry about that, but I hope you found it interesting. Many thanks then.